All right, so in this video, we're going to look at how to estimate the error or calculate the number of n that we need for a particular error using Simpson's rule. Now, the formula for Simpson's rule is going to be very similar to the one for the trapezoidal rule, except that we're using the fourth derivative for the function. I've used both versions of the notation that you may encounter. Some people use Roman numerals. Some people use 4 in parentheses rather than 4 primes because they're hard to count. So, but these are both the same function. Another difference between this and the trapezoidal rule is the power of b minus a, and then also our denominator is a little different. But basically, the idea is the same here. So we did an example with n equals 6 in the calculating the integral using the trapezoidal, using the Simpson's rule, but we're going to estimate the error using n equals 4. Now the fourth derivative, again, we're going to need to calculate it. So we're going to start with our first derivative, which is the original function inside our integral. Sorry, f of x is our original function inside the integral. And then f prime of x, we're just going to keep taking derivatives. In this case, we're just going to use the power rule. So 1 over x is x to the negative 1, and the derivative of that is negative x to the negative 2. And then the derivative of that is going to be 2 over x to the negative 3 power, x cubed in the denominator. And then the fourth derivative, however you want to notate it, is going to be negative 6 over x to the fourth. Now, the thing to keep in mind for our formula is that we are finding the maximum of the absolute value of the fourth derivative. So that negative sign on the front, we're going to ignore. And x to the 4, 1 over x to the fourth is a monotonically decreasing function. On positive values. So in negative values, it's increasing, but on positive values, it is decreasing. So the largest value, the maximum value of the function, is at the smallest x value in our interval. Again, keep in mind, if you have a more complex function, not something that's monotonically decreasing or monotonically increasing, it is possible that the maximum will actually occur someplace inside the interval, in which case you would need the fifth derivative, set that equal to 0 to find the critical points on the fourth derivative. Those don't show up often in textbook problems, but out in the real world, in the jungle, in the wild of physics, where you might need to apply these problems, there is no guarantees. So it's always important to kind of think about what kind of function you have, and if there are potential peaks or valleys inside the interval you're evaluating on, you do need to take those into account because you do need the maximum on the interval. But our maximum on the interval is going to occur at x equals 3, which is the smallest x value. So let's take our formula here, and we're going to start replacing values. The maximum on this interval is going to be 6 over 3 to the fourth, which is 81. And then b minus a is 7 minus 3. And then for n equals 4, this will be 4 to the fourth. And then what we're going to throw this in the calculator, see what we get. 6 divided by 81 times 4 to the fifth divided by, and again, parentheses is so important, times 4 to the fourth. Looks like I have everything. And I end up with 0.001646 ... So this is going to be a smaller error than the same error that you will get for the trapezoidal rule. And in fact, this is a smaller error than we got for twice as many n when we did this with the trapezoidal rule. Now, the other thing that we wanted to be able to do with the error formula is to use it to determine how many n do we need in advance in order to get an error as small as we would like it to be. So we're going to, again, use the same formula, and it's going to be used in approximately the same way, but with some differences. So the derivative portion stays the same. The limits of integration get evaluated the same. The n remains, and the error gets replaced with the actual error that we're trying to estimate for. And again, I've put the approximation sign in here because the n that we're going to get is going to be a threshold. And so sometimes I find working with the inequality to be somewhat confusing, and it always seems to me like it ends up pointing in the wrong direction. And so I just take it out. And then we'll put it back in when we're at a point where it's clear which direction we need. And so we're just going to do the algebra on this. We're going to multiply both sides by n to the fourth, and we're going to multiply both sides by 10 to the fifth in order to get everything solved and on one side of our equation. And if we do that, so this guy is going to go over here, but as a positive, and the end of the fourth is going to come out, and it is going to go over here. And so now we're just going to throw everything in our calculator and evaluate this and see what we get. So 6 divided by 81 times 4 to the fifth divided by 180 times 10 to the fifth. And what I'm going to get is, again, approximately 43139.9177 ... And now what I need to do is I need to take the fourth root of this. So you can raise this to the 0.25 power. If you raise this to the 1/4 power, make sure you're putting your power in parentheses. And what you end up with here in this particular example, sorry about the paging, you're going to get n is greater than or equal to, because again, remember, this is a threshold value, 14.3275599 ... Now, the thing to keep in mind, the n has to be an integer. You do not ever round normally. It is a threshold. This is the minimum n that you need in order to get the accuracy that you desire. If you round down, you may or may not get the accuracy that you want. And so in order to make sure that this is actually going to satisfy our requirements, we need to round up. Now, in the trapezoidal rule, we didn't care if we rounded up to an even number or an odd number. But in Simpson's rule, we have to have an even number. So in this case, it's not enough to round up to 15, because 15 is not an even number. We have to round to 16. And again, not normally. It does not matter if this is 14.0000001. You should round up. And so this will be n equals 16. Now, we did this exact error with the trapezoidal rule in another video, and we need a 244 n to get the trapezoidal rule to get that same level of accuracy. Simpson's rule is going to be much less work. 16 is still a lot of steps to do by hand, but it is nothing at all like 244. So the Simpson's rule is much more accurate with many, many fewer calculations that are required.